When you place capacitors in series and parallel, they change the way that they store the charge and the amount of charge that they can store. So we're going to look at analyzing a reducible capacitance circuit. Remember that the capacitance that we define to be the amount of charge that can be held at a particular potential difference. So in this case, we actually know how much charge, and we'd like to know the equivalent capacitance so that we can find the potential. So I'm looking at this and I see that there is a series of capacitors here. And so to find the equivalent capacitance, I take the sum of the reciprocals and then find the reciprocal of that. And that will give me the capacitance for that series. So that's this is 4/20ths. So I've got 4/20ths, 5/20ths. Take the reciprocal, that's 25ths or 4 microfarads. So this capacitor behaves as if between this point and this point here, it behaves as if it's a 4 microfarad. Now the remaining pieces of this capacitor bank are all in parallel with one another, so I can just add those. I've got 10 plus 4 plus 2 microfarads, and that gives me a total of 16 microfarads. So if there are 16 microfarads stored in this capacitor, then I can find the potential across the capacitor by looking at the ratio of the charge stored and the equivalent capacitance. So the question above tells me that the charge stored is 48 microcoulombs. We just found the equivalent capacitance to be 16 microfarads, so 10 to the 6 divided by 10 to the negative 6. 48 divided by 16, I get 3 volts. So when I come down here, this is a 3 volt potential difference. Now that we know this about the potential difference, we can answer some other questions and analyze the entire circuit. So back to this circuit, I've got 3 volts of potential. And so I notice that since this piece at the top and this piece and this piece are all in parallel, that the potential drop across there is 3 volts. So this side is 3 volts higher than this side. That allows me to think about how much charge is stored on each one of these. So if I want to know the charge stored, I go back to my original relationship, the charge stored per volt. And so if I want to know the charge stored, take the capacitance times the voltage. So for the 10 microfarad capacitor, it has a capacitance of 10 microfarads. There's a potential difference across it of 3 volts. And so that's 30 microcoulombs of charge. Remember, our total is 48, so 30 of it is being stored on the top capacitor plate. We move to the bottom capacitor plate. I've got the charge there, and so this is a 2 microfarad capacitor. It also has a potential difference across it of 3 volts. That means 6 microcoulombs of charge. Now I know the total is 48, so I know that between these two in the middle, the charge is the remainder, so 12 microcoulombs and 12 microcoulombs being stored there. But we can double check that. If we look at the charge on the 5 and the 20, then we know that the equivalent capacitance of those two, we calculated on the last slide, That was 4 microfarads at 3 volts. And sure enough, we get 12 microcoulombs. And when we add all that together, we get our total 48 microcoulombs. Okay, so we found out several things about this capacitor bank. We know that in order for it to hold 48 microcoulombs of charge, that the potential difference must be 3 volts. We know the capacitance values for each capacitor because they were given to us. And we know the potential difference across the 10 microfarad and the 2 microfarad because they're in parallel with the battery, and so they are getting 3 volts of potential. And so we actually calculated the charge on each one of these. So the 3 things that we can know: capacitance, charge, potential difference. We know those for those 2 capacitors. Here in the center, we know that the equivalent capacitance is 4 microfarads. We know that the charge on there is 12 microcoulombs, and we know that the potential across that is 3 volts. But if we want to know that for each individual resistor, we can find that also. One thing I know, since these are in series, that the charge across the 5 microfarad capacitor is equal to the charge across the 20 microfarad capacitor. They are wired in series with one another. So that's 12 microcoulombs. I know their individual capacitances, so I can find the potential difference across the 5. Don't forget our original relationship, Q over V is capacitance, so that means Q over capacitance is voltage. And so if we want to know the potential difference across the 5 microfarad capacitor, we would take the charge on the 5 microfarad capacitor and divide it by the 5 microfarads. So we've got 12 microcoulombs, 5 microfarads, and so micro divided by micro, I've got 12 divided by 5, which is 2.4. So 2.4 is the potential difference across this 5 microfarad capacitor. I know across the entire series is 3 volts, so that means there's 0.6 volts to maintain that 12 microcoulombs on the 20 microfarad capacitor. But let's show that mathematically. So the potential across the 20 microfarad capacitor is the charge on the 20 microfarad capacitor divided by its capacitance. So the charge was 12 microcoulombs. The capacitance is 20 microfarads. So 12 divided by 20 gives me 0.6 volts. And just as I expect, when I add those together, I get a potential difference of 3 volts. So there are actually quite a few questions that we can answer about this bank of capacitors. We also, now that we know the capacitance, the charge, and the potential difference for each one of them, we can do things like find the electric potential energy that they store. That's something that we just need to know Q and C. And so since we have those values, we can look at the potential energy. We could look at the potential energy for the entire circuit. And so let's just do that one. P total. Well, that's going to be 1/2 the charge that's stored, which we said was 48 microcoulombs. I'm going to write out the 10 to the negative 6 because I need to square this value. And then the net capacitance when we were all finished here, we said that's 16 microfarads. And so again, I want to put the 10 to the negative 6 in there. And 48 microcoulomb squared divided by 16 microfarads, and then divide by 2, and I get the potential energy stored is 7.2 times 10 to the negative 5th joules. Again, I can take each one of the components and figure out which one's holding how much of this energy, but I'd use this same relationship. So more questions that I can answer about this capacitor bank.